Welcome everyone to Combination Colonial Linux User Group, Upstate Carolina Linux User Group presentation of Blockchain Without the Hype, presented by Caleb Power. Caleb, take it away.
All right. Hello, everyone. Let me see if I can get my screen to share itself. Can everybody see that? Pretty all right?
Jay says he wants to speak.
Oh, yes.
Go ahead, Jace. He doesn't have a micro camera. Okay. Oh, no, that's Arnold. Okay. Uh, ask to unmute. Okay. Uh, did you mute everybody, Caleb, or something? Or
Don't believe
maybe
so.
I'm clicking on ask to unmute and all right, Jace, can you talk?
Yes, I'm sorry.
Okay.
I did mute everyone as per default, but I muted myself as well. And I think it looked like Caleb either we had a bad connection here or Caleb was having a bad connection. Caleb, are you there?
Yeah, I'm here. Can you hear me all right?
I can now.
All right. And full disclosure, it looks like the snow is setting back in. So whether or not my internet is going to hold up, we'll figure that out as we go, I suppose. Um, but okay. So we'll try to screen share again. All right, can everybody see that all right? Yes,
Yep,
no?
I can see it.
Okay, perfect. All right. Let me move this silly little thing out the way. All right, so this is Blockchain Without the Hype. My name is Caleb Power. I run a small R&D organization called Axonobyte Innovations. See if I can move. I basically went to school for computer science and software engineering and digital forensics. So basically, in the day, I do a lot of stuff with the Oklahoma Medical Research Foundation. They don't do blockchain stuff, so obviously anything I say here doesn't really, pertain to them. But at night, I do basically custom software engineering with Axonobyte Innovations, and I do a lot of distributed node management through DNOT, Distributed Node Operation Technologies. So what I'm really going to try to cover today, and I'm going to try to, have this stretch to the hour, but we'll see how successful I am, is I want to talk about just the technical side of blockchain. I want to talk about data structures and consensus algorithms. I want to talk about how one might use blockchain and what that looks like in a traditional environment. And I kind of want to talk about, some things, some gotchas, and some things to look out for. But what I'm really not interested in right now, for our purposes, is I'm really not interested in any of the hype that we see in the news. I'm not really interested in, the best NFT on the market. I'm not interested in talking about hodling or FUD. I'm not interested in talking about, whether or not I should be investing in Ethereum or Bitcoin or whatever. That's just out of scope for today. Um, so what I'm really interested in is what are the underlying mechanisms, the things that would interest, somebody who is in this space. So yeah, that's just like I said, let's talk about the tech. I don't really care about the products, and honestly, a lot of the products disappoint me to some degree. So blockchain, what is as any as any tech develops, you have to ask, why would I want it? Am I building it just to build it? What is the purpose and what is the goal of building out blockchain technology? And in this case, we're talking about designing and implementing something that is immutable and tamper resistant, that can be used to verify a set of transactions in perpetuity. So what does that actually mean for our purposes? Well, here are some applications that you might use, or here's some applications that you might want to use blockchain for. The big obvious one is banking transactions. How do you prove that Alice sent Bob something, and how do you prove to the world that that happened, and how do you give Bob the assurance that they actually received some like cash or whatever? But I've also seen it used theoretically and in practice through like credential publishing. How do you prove that you got a degree at some university whenever you go to a job? How do you they really need to trust your resume, or can they check some online immutable verifiable database for your credentials? I've seen it used for governance. I've seen it used for in voting applications. I've seen applications for royalty management. How do you go about publishing some content and being assured that you're going to be paid for it if some other artist uses your content? I've seen it used for managing companies. I've seen it used for implementing legal workflows. So there's a lot of without talking about actual products behind the scenes, the actual use of blockchain as a data structure. And somebody's going to have to tell me if somebody's raising their hand or something, because I can't see Jitsi off of the top, but I'm hearing pings.
Okay, Jace would like to speak.
Yeah.
I was just curious what the ZPK and DAO stand for.
Yes. I won't talk about ZKPs and DAOs and DAOs so much in this, but in this case, a ZKP is a zero knowledge proof. A zero knowledge proof is a mathematical mechanism by which you can be reasonably sure that one party knows the answer to a solution to some problem without you, the verifier, needing to know like the answer yourself, right? And one of the I'm trying to think, one of the ways that they prove, or I guess one of the analogies that they use is, let's say that you are Alice and you are trying to prove to Bob that you can navigate your way through a cave. And actually, perhaps I should pull up Microsoft Paint or something. I tend to be a little bit visual. You're going to have to forgive my bad drawing skills, but can you all see this Microsoft Paint?
Yes.
Okay.
Yep, we got it.
Let's say that you are. I have my Wacom tablet downstairs or Wacom, and I'm just we're just going to deal with the trackpad today. But let's say that Alice asks their friend Bob, prove, this is my beautiful picture of a tunnel, prove that, and here's Bob. Okay, let's say that Alice says to Bob, hey, Bob, prove that you have the key to the door. Prove that you are able to open this door, but do not show me the key. Well, Bob can do this by, asking Alice to randomly pick one of these entrances to the tunnel. And then all Bob needs to do is traverse the entire tunnel and come out the other side, right? and I know that's kind of like a silly concept, but a ZKP is basically a mechanism traversing the tunnel by which Bob can prove that they have the ability to open the door without actually proving to Alice that they can open the door. And I can go a little bit more into depth after the talk on zero knowledge proofs and what that actually might look like. But in this case, let's say that you are setting up, a legal structure, and you want to be able to vote on things, and you want to, you want to prove that you voted, or you want to prove that a certain candidate or policy got a certain number of votes, but you don't want to basically dox anybody. You don't want to call out anybody for having a specific vote. Well, you can, be reasonably sure that an individual received a certain number of votes without, actually, revealing somebody through zero knowledge proofs. And I know that ZKPs kind of sound a little bit like mathematical magic whenever I explain it at such a general level as that. But I am happy to go more into depth on that.
I was simply asking what the ZKP stood for, just because I'm not in that space. But it makes sense. And also just wondering what DAO, because I don't know it by heart what that means.
Yeah, a DAO is
I did not mean to go down this rabbit hole that you're not wanting to go down.
Oh no, you're perfect. And I told Ben earlier, I'm really bad about rabbit holes. I will absolutely take a tangent. So don't feel bad if you make me go down a rabbit hole. And if y'all want me to go back on topic, just yell at me. But DAOs are distributed autonomous organizations, basically a company that lives in the blockchain. So, most companies have to have some sort of legal presence. Question is, can I control the operations of a company without being beholden to, a legal structure? And a DAO is one way to do it. Now, the legalities of having a DAO are up to question, depending on your jurisdiction. So I won't touch a whole lot on DAOs now, but it might be something that one might consider doing if they wanted to, or it might be a reason somebody would use the blockchain, if that makes sense. So, just to package that all up nicely: ZKP, zero knowledge proof; DAO, distributed autonomous organization. I hope that sort of clarifies both of those terms.
Thank you.
Mm-hmm. Okay, so blockchain, there's 3 points here. Blockchain is not new, is really what I mean by this first bit. It's not, somebody may have come up with putting all these technologies together, but anybody who is in any space knows that technologies are built on the backs of others. And blockchain is no different. It is really just an amalgamation of a bunch of older technologies that we will see. So whenever I'm talking about data structures, I also want to make a point that I will be generalizing a lot, because there are so many forks that every implementation is slightly different, and there may be a lot of whataboutisms. What about this instance? What about that instance? Well, yes, probably. So the data structures that I'll be talking about can be manipulated one way or another, and I would just keep that in mind. And lastly, this is the first time I've talked with you guys, so I don't know where everybody is at. So some of these terms and definitions may be super old news, so just bear with me on that. So some things just to brush up on is familiarities with hashes, linked lists, and binary trees. Which will be pretty relevant as we look more into the data structures. Hashes, I think a lot of people are in the Linux space are familiar with checksums. It's basically a hash is the result of the mechanism used by which somebody takes a datum and processes it such that it results in a fairly dispersed fixed length result. And most people use this for verifying that a datum has not been modified. Linked lists, a data structure, it's linear. You have one node that connects to another node. If you're a C++ developer or a C developer, most of the time people do this with pointers. And binary trees are data structures which are generally used to optimize search operations where nodes are arranged in a tree-like form. And feel free to interrupt me at any point if I need to clarify anything. So with blockchain, PKI and public key cryptography should probably be known. So you guys are familiar with symmetric key cryptography. I hope, encrypting and decrypting something with the same key. And obviously anybody who logs in with RSA keys or ED25519 type keys for SSH on a Linux system has used asymmetric cryptography, where something is encrypted and decrypted with a mathematically linked yet distinct set of keys. So along those lines, one of the things that if you're in the blockchain space, you should probably be familiar with are signatures, which are, of course, a special type of public key encryption where the hash is signed by a private key, right? So that anybody with the public key of Alice, for example, can verify that Alice actually sent a particular message. So these concepts are relatively important whenever we're talking about blockchain. So here's just to get through our review pretty quick. Here's just a diagram of how one might go about, creating a signature and verifying the signature. Okay, so review out of the way. Here's some things that you might consider learning for blockchain. So let's take the example that Alice sends Bob $500. Well, that's implied to be a transaction, right? Built of a set of ordered actions. What do I mean by that? Well, what does Alice actually do whenever Alice is sending Bob $500? Well, Alice is first withdrawing $500 from their bank account, and then they are sending that $500 to Bob, and then Bob is receiving the $500 and depositing it into their bank account. So really three different actions: withdrawal, sending, and deposit. So these are, these actions atomic in nature, such that if one action fails, the entire transaction fails. Whenever you group each individual action together, it's called a transaction within the scope of blockchain. So for the way blockchain works is blockchain networks process, sets of transactions discretely, right? What I mean by this is that let's say that you have a bunch of people sending a bunch of other people a bunch of transactions, right? It's not streamed. It's not like the blockchain processes every single transaction that comes through whenever it comes through. Instead, groups of transactions are processed sort of in batches, and each of those batches is referred to as a block. And whenever you consider the processing of a bunch of individual blocks together, this linked list that results is called a blockchain. So that's kind of one of the main things that I want to kind of get into everybody's head at the very, very beginning of this thing, is that blockchain as a data structure is not a difficult data structure. If you are already familiar with linked lists, it's really just a linked list under the hood. Every block knows, and I'll talk about what this means in a moment, but every block has its own checksum, and every block knows the checksum of the previous block, right? So what might that look like? Here's kind of a blown up picture of what the first 5 blocks of a blockchain might look like, right? And remember, I was saying that every block is sort of a set of transactions, right? I don't know if you guys can see my pointer or not. Remember that blockchain is really all about verifying that transactions on the ledger are accurate and true, right? So as this data structure grows, as you're adding more and more transactions to the master list you're calling the ledger, you want to be able to prove that every set of transactions up to that point, the entirety of the set of transactions before that point are legitimate and true. So every block will actually have a record of what the hash of the block previous to it is. So let's say that somebody modifies maliciously block 2, right, resulting in a different hash. Well, as more blocks are added to this data structure, you'll end up with a hash mismatch, which essentially invalidates the ledger, if that makes any sense. So how do you go about coming up with this mystical block hash? Well, in general, every block, remember, it's processed discretely, maintains some metadata, the hash of the previous block, the time at which that block was executed, maybe some individual datum associated with that individual block, and then this thing that we're calling the Merkle root. And if anybody here is already familiar with binary hash trees or Merkle roots, then this won't be any news to you. But we'll talk about that a little bit more in a second. So does anybody have any questions up to this point? I know that's kind of
I do have a question.
Yes.
Okay, so the transactions are coming through as blocks. What happens if I keep sending money that I don't have? Can you talk about, the process of what happens if the transaction fails?
Yeah. So a lot of times that differs on a lot of times that the way that mechanism is actually handled is dependent on the implementation, right? Generally, so this like a blockchain itself is just the data structure and doesn't necessarily handle the balances. Later on, what we'll sort of talk about is how blockchain is sort of the hardware upon which a distributed operating system sits. And this distributed operating system will have programs on it to actually check to see whether or not you have a negative balance already. So, I was talking about actions. One of those actions might be to check to see what your balance is, and if your balance is, not below, or if your balance is would be below 0 if you were to send your desired amount, then to kill the transaction. Sort of like a failed assertion, if that makes any sense. But yeah, a lot of those questions of validity. Does this person have enough money? Does this person have permission to do X, Y, or Z? Does this person, whatever? A lot of those questions are actually handled a little bit higher up the stack than the actual, the actual verification that the data structure itself provides. Does that make any sense at all?
Yes, thank you. Makes sense. I was just wondering, like if I tried to send this person 500, and then I tried to send that person 300, but I only had 400 in my account. I guess it's just gonna fail if it's the 500, and maybe go through if it's a 300 or something like that.
Are you asking, like, since these are processed discreetly, if I were to send 2 transactions of amounts A and B, where A and B put together are bigger, would it be able to catch
Yeah.
Yeah. A lot of those are. So the quick answer there is yes, definitely. Blockchain is most blockchain implementations, and I believe all should do this. Will catch that sort of thing, so that you're not just like, suddenly using up all of your account balance with a bunch of microtransactions. That is accounted for. I don't know off the top of my head what the technical implementation is for that at the data structure level. I can look into that though, and kind of report back with what I find.
Well, let me
Thank
ask
you.
let me ask a kind of a similar question. In your example, you said if block 2 were changed somehow, then in this block 3, previous block hash would be a mismatch with block 2's hash.
Mm-hmm.
Do you know if most implementations would say that block 3, 4, and 5 are now invalid, or what happens? Is that a new tree, a new blockchain, or?
Yeah, actually, depending on the implementation of blockchain, you can get what's essentially called forking. The kind of terms, blockchain terms, are kind of synonymous with how we would refer to a Git repository almost. Because if you think of like a Git repository, each commit is sort of like a block if you really squint and look at it, through blurry vision.
Yeah, Git uses a Merkle tree underneath too. So yeah.
So like you can get to points where there are, and I'll talk a little bit later about the big elephant in the room, which is I haven't even talked about, having multiple nodes yet. I'm just talking about like a data structure on one local machine. But yeah, you can definitely get to a point where you have multiple nodes working together, and some of them disagree with the others. And what do you do about that? Does the blockchain just fork itself and it's suddenly a new network, or not? So some blockchain implementations will allow for that sort of thing. Some of them terminate themselves if they detect that. Most of the time, what ends up happening is you have mechanisms in place to prevent that from happening in the first place. And we'll talk about consensus algorithms in just a moment. For this, I'm mostly talking about the theoretical, here is how one might tell that a blockchain is invalidated, rather than the practical, here is what a blockchain implementation will do. And I tend to I tend to avoid the hard answers on implementations, just because there are so many implementations on what a blockchain network might do if it happens to run into a hash mismatch. Does that sort of make sense? The motivations and the answer.
Implementation specific is what you're saying. Yes.
A lot of times, yeah. A lot of a lot of times you'll run into like YouTube videos will go, blockchain does this, and it's like, well, sometimes it does that. Maybe Bitcoin does that, but what about the more modern ones? But yeah, and if this is a topic that interests people, in general, I can definitely pull some more material together and talk about the specific instances like soft forks, or like truly granular atomic handling, that sort of thing. Okay, so this kind of image is sort of how do we validate or verify that a block matches a previous block, but we kind of skipped over Merkle roots and how do you validate that? How do you get hash for a block in general, right? How do you determine that a specific transaction in a block is appropriate? I kind of want to say the words Hamming codes to people so that if you know what Hamming codes are, then it'll kind of like you'll have an analogy in your head already. Okay, so what? Every block has a set of hashes, right? And every let me back up. Every block has a set of transactions, right? And you're trying to from all of those transactions derive a single hash for the block. How do you do that? Well, you could append the hashes of every transaction together and then hash that, right? But that would be problematic if you were trying to narrow down which transaction failed, right? Let's say transaction 5 here, Alice sent Bob $500, and some bad actor comes in and goes, actually, it was $1,000, right? Well, okay, if that's the bad transaction and you're going back and with this block hash and trying to figure out which transaction is actually the bad one, you have to send data for all of the accompanying transactions, right? In order to figure out which the transaction 5 is the bad one, you'd have to take the hash of transactions 1 through 4 and 6 and 7 and compare it with transaction 5 to determine that that indeed was the bad one. And you can imagine that that becomes problematic down the line whenever you're trying to analyze Merkle when you're trying to analyze a block as a data structure. So what they generally do instead is they use Merkle trees, where instead of appending every single hash to every other hash and then getting an aggregated hash, what they do is they'll sort of break it up. You can think of it like a merge sort, almost, not a sort, but it's a binary tree, right? Where they actually will take 2 transactions, every 2 transactions, and bottom up merge them, right? So get the hash of every transaction, append 2 transactions at a time, get the aggregated hash of those 2, and so on and so forth, right? And what ends up happening is that if you have a transaction that is, bad, then really all you need to do to verify that particular transaction is get the hash of or aggregated hash of every transaction that is not affected by that, right? So we see here, I've actually labeled transaction 3 as being the bad one. So what do you need to do to determine mathematically where the mess up is? Well, you really just need the hash of transaction 4, because that's essentially 3 hashes sibling. You need the hash of aggregated 1 and 2, and you need the aggregated hash of 5, 6, and 7. So I was kind of mentioning Hamming codes earlier. If you are familiar with, how error handling, and my brain is just not working on terms today. But if you're familiar on how error correction works in general, you might recognize this. You might recognize why fewer hashes are needed as opposed to every single transaction being resent. So does kind of everybody understand Merkle trees just at a very basic level at this point? Okay.
Yep.
Sweet. So as you guys have sort of guessed probably by now, and we've kind of already talked about it. You can take a look at the data structure all you want and verify elements of that data structure all you want, but it really doesn't matter if it's all running on one machine, right? Because that one machine could just change the message and the associated hash and recalculate hashes up the chain. And that, okay, fine, whatever, right? So what you actually need to do is you need to, if you're implementing a blockchain, in order to ensure that it's immutable, you actually need to compare it with a copy of the ledger on a bunch of different nodes. So what you get, 5 nodes working together, and they all have copies of the same ledger so that they can compare it with each other, and make sure that one node didn't just often create its own data. So what ends up being a large problem in computer science as it pertains to large numbers of nodes is the notion of consensus, right? How do you know, or how do you go about adding new blocks? How do you go about determining how many nodes are needed to agree on something? How do you go about, verifying each and every block without making it a really big, n squared connections problem, or n factorial rather. So what they've come up with are consensus algorithms, which are basically just algorithms used to establish a collectively shared truth. And most of the time, whenever you see consensus algorithms in the wild, you'll see them referred to as proof of blah, right? Proof of work, proof of stake, proof of space are all consensus algorithms that are used in blockchain to sort of make sure that the network isn't being spammed with new blocks, make sure that blocks are being added to the chain in a sane way. The little side note I have here is that, in reality, blockchain is, is something that's heavily marketed, and people have latched on to proof of whatever, right? Much like they've latched on to blah as a service. So not everything that is proof of foo is going to be a consensus algorithm, but most things that are consensus algorithms in the blockchain space will be proof of something. So before I really go on to consensus algorithms, and somebody may have to yell at me if I'm getting close to time because I have no idea where my clock went. Before I go into consensus algorithms, I kind of want to take a step back and make sure that everybody here isn't really like getting tricked into believing that blockchain represents parallel computing, right? Because whenever we think of parallel computing, we think about large matrix multiplication problems that we can split up and distribute to a bunch of nodes in an HPC cluster, right? Or we think about large merge sorts that we can recursively solve. Blockchain is not parallelizable. You can't take a block and break it up and solve it amongst a bunch of different computers. And in fact, it's almost the reverse of that. Instead of one problem that you're splitting up and solving on individual nodes in a network, you are taking the same problem and solving it a bunch of times on a bunch of different nodes in the same network. So instead of like saving compute resources and saving storage resources, you're actually compounding it in the name of redundancy and separation of authority. So I would keep that in mind, that as I move forward in this presentation, whenever I'm talking about distributed networks, I'm not talking about parallelizable networks, problems. They're two separate things. And in that manner, you'll a lot of times hear about the scalability of blockchain. But whenever I'm talking about the data structures that make up blockchain and the storage required for blockchain, that is not really scalable. So I just keep that in mind as we move forward with our talk on consensus algorithms. So consensus algorithms, well, we're talking about how do we come up with the shared truth, and what are we trying to avoid? Why not just prevent against the split head problem? Well, we're also trying to prevent what are called Sybil attacks, which are what you get a bunch of nodes and you attach them to the network, and suddenly you have a majority of nodes on the network, and you can take over and determine for yourself what the shared truth is, so to speak. And depending on the blockchain network, this doesn't necessarily mean the number of nodes attached to the network. It can also be the number of accounts created on the network, or the amount of token ownership you have on the network. It can come in a lot of different forms. So a good consensus algorithm will be resilient to these sorts of attacks. So we'll sort of like jump real quick into what kind of consensus algorithms there are. The most famous one is proof of work, because Bitcoin uses this, and this is why Bitcoin gets a ton of flack for being power hungry, and it's because it is, right? Lots and lots and lots of people mine Bitcoin, because the mechanism by which spam is prevented on the network is proving that you have the computational power, power necessary to mine a Bitcoin, right? But actually, proof of work is, and at the beginning of this talk, I said, blockchain is built on the backs of people who wrote older technologies. Proof of work is one of them. Proof of work was originally to prevent network spam. I can't remember if it was email specifically or not, but it originally was not blockchain related at all, right? Obviously, proof of work, a lot of people have been trying to get away from it, trying to find a similarly secure algorithm that is a little bit more eco-friendly. And so people have also come up with other ones, and I'll mention like proof of stake and them in a second. But yeah, proof of work, you'll hear some terms thrown around like miner pool, and that's just referring to creating the blocks to put on the blockchain, who creates those blocks, different ways, why people, different methods by how people might profit share. So yeah, one of those alternative methods that people might use, another consensus algorithm, is proof of stake, wherein people are encouraged to not spam the network, because if they do, they may actually lose some of their stake being some amount of token that they have in the system. So this is a little bit more popular. Ethereum uses this now, I think, with a version 2 of Ethereum. A lot of times you'll see really, really fast blockchain networks use something called delegated proof of stake or similar, where instead of being chosen as a validator, and I'll mention here, instead of being chosen as a validator for that network based on how much money in the system you have, you instead get to elect sort of a senate to validate on your behalf. So, with Bitcoin and Ethereum and most traditional proof of work and proof of stake chains, you're involving a ton of nodes, right? A ton of nodes which must share with each other the same source of truth in order to, prove that your transaction and your block is correct. And it's a lot of machines globally, right? These alternative POS derivations, like delegated proof of stake, are sort of designed to make that process easier so that you're not waiting around for your transaction to be verified. And then you also have like proof of space, which is sort of like proof of work, but instead of proving that you have the computational ability to do something, you prove that you have the space to do something. But remember, all of these consensus algorithms really are just answers to the question, how do I go about proving the shared truth without spamming the network. Okay, so let's take a step back from like consensus, because we can really get down and dirty with the consensus algorithms, and people love building vanity algorithms, and it's just not always worth getting into. But whenever we're talking about, when we're shifting a little bit more into the sysadmins to this, I always think of a protocol as like a suite of theoretical tools, right? Like a TCP/IP protocol. It's kind of redundant, but or the IP protocol or something like that, HTTP. In blockchain, it's a little less theoretical. You do have the mechanisms and the API documentation and the algorithmic implementations. But a lot of the times the blockchain protocol is also the actual reference implementation associated with those theoretical writings. So you'll see blockchain protocol thrown around a lot. Really, they're talking about the Ethereum blockchain protocol, the Bitcoin blockchain protocol, the EOS blockchain protocol, that sort of thing. But my point in mentioning that is that blockchain protocols do not have a one-to-one relationship with the networks that get spun up, right? It's like saying a blockchain protocol is Google Chrome, but that doesn't account for the number of times Google Chrome is launched on a computer, right? So a blockchain network many blockchain networks can be spun up from a single protocol, and sometimes it even makes them more compatible with each other. A lot of the times in the real world, how they refer to network implementations that have been spun up with the purpose of having a token that is worth something, right? Something you can trade. They call that a mainnet, right? The Ethereum mainnet has Ethereum tokens that can be sold and bought. But of course, you can, as any good developer will tell you, you should probably test your product, and because of that, test nets can be spun up as well. So somebody was asking me about how might you go about checking people's balances beforehand, and how might you go about validating a user's permissions and stuff. We should probably keep in mind that modern blockchain for the nowadays supports what we call smart contracts. And smart contracts kind of sound weird, but really it's just executable code on top of blockchain. Some of them are fully Turing complete. And some people might go, they can't be fully Turing complete. They don't have a timing mechanism. Some blockchains actually do have a timing mechanism that allows for future execution and are actually fully Turing complete. A lot of blockchains can even be compiled from standard languages nowadays and just execute WebAssembly directly, which is actually quite interesting as we're looking at this in more of an abstract lens. So, I've tried for this talk to, and I failed a little bit at the beginning, but to try to stay in the general, to generally describe the data structures of blockchain. But you got to understand that there are tons and tons and tons of things we could talk about, because we're essentially talking about a distributed operating system at this point. And the disciplines kind of go out of the scope of a systems administrator and into the scope of people interested in financial technology. Whenever we start talking about smart contracts and the algorithms required to regulate markets, regulate inflation, regulate rewards and commission. So that is something we can talk a little bit more about. It goes out of scope for what I am very familiar with. But it is sort of akin to, asking for a blockchain talk is a lot like going and saying, what's your degree in? Oh, I have a degree in science. Well, it's just too broad nowadays. But we can talk a little bit into about systems operations for blockchain. And the biggest thing to remember with blockchain systems operations is that it's not, as I mentioned at the beginning, it's not new, right? It's actually way more traditional than one might guess. So best practices in information security apply, best practices in systems administration apply. And as those of y'all who are doing this for work probably know already, most people do not employ best practices. And so whenever you're talking about blockchain implementations that take a lot of global coordination to set up, and you kind of juxtapose that with people who just don't generally apply best practices in general, you can imagine that that might be a little bit frustrating and the brunt of what one might face if you're entering, blockchain sysops from a more traditional, occupation. But it might also be interesting to take a look at like what do we mean by a distributed operating system in this case. And so I've sort of fudged together what we might think of as a local stack and a chain stack, so to speak. So on a standard general operating system, right, you've got your server hardware, your actual the bones of your machinery, and on top of that you generally have your kernel and the privileged side of the operating system, and on top of that you've got your user land stuff, your programs, things that are maybe like critical software but are not necessarily like kernel space. And then on top of that you've got your general programs, including like your blockchain node, the agent that might sit on your physical machine and peer with other nodes. And I kind of wanted to draw a parallel to the actual distributed operating system on top of blockchain, whereas your blockchain node is on the local stack and application. If you're looking at it on the blockchain side of things, on the chain stack side of things, it's really the hardware, right? The abstract hardware. It's a set of, like OSI level 1 protocols, if you want to think of it that way, or 2 rather. Like it's how do these nodes physically connect to each other. And on top of that, you have your consensus layer, your consensus algorithms, your proof of work versus your proof of stake, the actual meat of the problem that makes that grows the blockchain and actually performs validation. And then on top of that, you have your system contracts, which is sort of like the beginnings of your user land space, right? The components that are technically programs and applications on top of the blockchain that the standard user would not, manipulate themselves, that govern things like permissions and balances and stuff like that. And then on top of that, you have your user contracts. What smart contract can a user of the system submit and run themselves? So they're not quite one-to-one. But I'm hoping that when looking at this, we can sort of see the similarities between, the like a local machine, and sort of treat blockchain as a shared virtual machine, like a global virtual machine in some cases. But like whenever you're actually deploying this thing, your tools of the trade are going to be pretty similar, right? And your best practices are going to be pretty similar. Like at DNOT, we use Cloudflare and HA proxy for DDoS mitigation and load balancing with HTTP APIs. For things where there is not like an appropriate application firewall, we use other nodes in front of nodes to sort of provide that sort of buffer. We use monitoring. We use our in-house, DNOT Chain Spy, but we also have Grafana dashboards, and there are Prometheus endpoints that we pull off of. A lot of blockchain runs on Ubuntu, usually the LTS versions. So a lot of if you're going from traditional systems administrative work to blockchain systems administration work, a lot of the tools are fairly similar, and it's not a massive leap. Is really my main point. But there are a couple things that you do have to consider. If we're taking a step back and just like doing the actual architecture of a network, and we're trying to figure out what resources we need. And one of the big things that people for some reason forget is that the blockchain is immutable, right? Usually. A star asked me about this later. That's not always the case. But because blockchain is immutable, you have to figure out how you're going to keep adding disks to your system, right? You can't just go grab a 50 gig hard drive or whatever and call it a day. So if you're running enterprise solutions, you might consider actually building out like a Ceph cluster or something. So, storage considerations are, something that may be a little bit more unique to blockchain deployments that one might consider. One might also consider, geodistribution. How are you going to, and this is a little bit, less specialized nowadays with the advent of CDNs. But how do you go about serving everybody on the globe? This thing is supposed to be distributed and decentralized. How do you go about making sure that the centralized components of your blockchain are actually in places that people can use? A lot of communities don't do this very well, and it results in pretty brittle blockchain networks. And then the other thing to remember is that blockchain implementations are not the end-all, be-all tool. I'm not a very big fan of people who use one tool for everything. I've always been of the mind that you use the tool for the job, and blockchain is a tool. And if you use it for the wrong reasons and you use it as the wrong tool for the job, it's not going to work out very well for you. So as an information security engineer, there's a few things that one might consider. We've already talked about Sybil attacks, but you also might consider, especially whenever in the US at least, blockchain regulation is not modern currently, what things can and cannot go on the blockchain, right? Even in terms of privacy, even in terms of, if you're talking about the GDPR out in the EU, how do you get rid of data that has been stored on an immutable data structure, right? And then on the more fun side of information security, be aware that blockchain is inherently a tool used to propagate data. So that's, very fun for people who are into exploiting covert channels, propagating malware, or finding, especially for those fully Turing complete machines, executing arbitrary RCEs. And then the other big thing is that, remember that blockchain systems are, like I said, not parallel computing devices. They're supposed to be redundant, but they're redundant on a local level, right? The machines are redundant, and they work together to create one big distributed operating system, which means that distributed operating system is not redundant. So if you push an update to a blockchain that is supposed to be like a big system contract update and affect every node at once, you're going to have a bad time if it's not bug free, right? So basically the last few slides here are, don't forget that this isn't a solution to all of your problems, and in many cases it creates new ones, which might be interesting. And as with most software, the biggest method of prevention is quality assurance. So yeah, there are some takeaways here. Blockchain tech, it's old technology. It just is put together in a new way. It's fairly easy to get into blockchain sysops. Most of the infra is traditional, and a blockchain is not an excuse to be lax on best practices. Here's some topics that I didn't cover. So I didn't touch at all on actual, Web3 implementations or smart contract security. I didn't talk at all about tokens. We talked a little bit about governance and DAOs, but we really left it alone for the most part. So I know that was a lot of information all at once, but if anybody has any questions, now's the time.
We have a question here.
Okay, my question is how do they typically do updates? Or you talk about forking? Do they build that into from the manufacturers, the blockchain or something?
Yeah, so updates vary. I know somebody here is going to be tired of me going, it's just implementation. So I'm sorry, don't hurt me. But yeah, so it depends. Some of them, generally, blockchain implementations and reference implementations are sort of held by some community organization. I tend to call them foundations. And they will update the code and then politely ask a lot of the validators or miners to pretty please update your binary. And then whenever the binary is updated, and the consensus mechanism is adjusted such that most people are on that binary, a lot of the times that is what results in the network update. Sometimes. I believe, I want to say that Bitcoin does that. I want to say that I think Fuse does that. I can't recall off the top of my head. Some of them, whenever we're talking about the abstraction of virtual hardware and virtual operating system, like the chain binary versus the the system contracts, right? And when we're talking about those situations where they don't want to upgrade the binary, but they want to upgrade the system contracts, a lot of the times that just happens through the execution of a vote through some pre-existing governance. Sometimes what happens is the foundations update the binary, say, hey, we are stopping at a certain block height, and you better update, otherwise you're going to crash. So there's just a ton of different ways for the actual underlying mechanism of updating the quote unquote global distributed operating system for whatever chain you're talking about. Invariably, they almost always require, especially for the delegated proof of stake versions where you have a small number of validators, they almost always require everybody to jump on a Discord call or a Telegram meet or something like that to actually coordinate upgrades. Did that sort of answer your question at all, or was I completely off base?
Yeah, I think it did. I was just kind of wondering how that's like differentiated between like an adversary trying to say, oh, this is actually the new binary that gives me all the money or something.
Could you rephrase that just a little bit? I'm so sorry.
Yeah, I was just wondering like how like the foundation updates are different than like an attacker saying, oh, actually this is the new binary and the new binary is my custom,
Yeah. Yeah, it's okay. So the best way I can answer that is like most decentralization is a lie. So what I mean by that is you think that the internet is decentralized, but it's not, right? Like it's like the root keys are held by a small group of people, right? So it really is there a mathematical means by which people can be absolutely certain that these are good actors deploying binary upgrades? Not mathematically, but there's a lot of best practices people put in place, right? Like people will tie their identities to the chain. They'll say, hey, look at my Keybase identity. I've stored this on the chain. So if you see a message from this Keybase identity, then maybe it's probably legitimate. Or they'll share beforehand, hey, this is the GitHub repository that will have, new upgrades. And so if you see an upgrade from a different location, then you should probably not use that binary. At the end of the day, upgrades, especially, like I said, when we're talking about, when we're talking about these mechanisms to sort of verify, which upgrades are good. They really come down to an individual's ability to ascertain that that the upgrade is legitimate, coming from a legitimate source, is not the result of some bad actors campaign and such and so forth. And these validators are generally incentivized to make sure they're doing things correctly as well, because if they break the chain, they lose all of their stake, or they lose what hard work they put in, or they lose the ability to make rewards and commission off of something. But yeah, no, you're right. Theoretically, somebody can go in and be like, here is a bad update. I'm a good person, trust me. And like, yeah, technically that might happen. Would it happen in practice? People tend to be pretty vigilant on that. But there are some communities out there that whenever a security issue happens, they go, here's my new binary update. Trust me, you know. And I usually am pretty loud about that kind of thing, because I tend to think that, you know, if there's a security upgrade, we should probably review the source code before implementing new stuff. So yeah, I mean, you kind of hit on the you know, on the topic of, yeah, at the end of the day, everybody is people. There's not really a mathematical means by which you can guarantee that the upgrades are correct. People just kind of have to, you know, Swiss cheese model the best practices on top of each other and make sure that they're being vigilant. So,
If I remember correctly, there was a big hoopla or something whenever Ethereum changed either version number or from proof of work to proof of stake or something like that, which took a long time to happen, if I remember correctly. Is that right?
Yeah, and I wasn't as strongly involved with a lot of that stuff. But yeah, I mean, from what I understand, Ethereum, or the folks that run it, have for a long time been trying to get away from proof of work and more into proof of stake. And they didn't really want to, like, you know, well, they're running into two problems, actually. The first one is the consensus algorithm, because it's very power hungry, and you'll by design, and you'll see a lot of people go, but eco credits, or whatever they call those, and I usually just kind of laugh and wave that off. The other thing is that blockchain is not scalable; it's anti-scalable. Like the actual blockchain implementations, like they're scalable, but like whenever you're copying the same data set a whole bunch of times to for you know, redundancy, so to speak, it makes it difficult to really increase your throughput, right? And so you have this concept of, like, it's vertically scaling. How do you, you know, make it to where your chain that has a hard time being fast in general, that requires a bunch of redundancy, how do you make it to where you can add a whole bunch of new users without slowing everything down? And so the option here is horizontal scaling. Spin up another blockchain and then write a mechanism where they can talk to each other, and then make it expensive on the original blockchain so that people are incentivized to go onto these other, you know, child blockchains and then do that. And so Ethereum kind of did both of those things. They were like, I want to move to proof of stake, and I want to implement a mechanism by which we are encouraging horizontal scaling. And they've sort of done this. I'm not really sure what point they're in, like what point they are at this point. But they sort of have said, okay, here's the original proof of work blockchain. Here's our new blockchain. The proof of work one is like the main blockchain. Now we're going to make the proof of stake one the main blockchain, and the proof of work one is going to be, I think they call it a shard. I can't recall quite, but the proof of work one will be one of our horizontal scaling blockchains. And also we're going to encourage people to create their own horizontal scaling blockchains and connect them all together. And now we're going to make proof of work really, really expensive. So people don't use that particular offshoot and they start using everybody else's. So as you can imagine, and because there are lots and lots of people who mistrust proof of stake, because they feel like proof of work is more secure than proof of stake. You can imagine this massive upheaval of just the, you know, the topology in general, and the swap to proof of stake, and all of that has miffed quite a few people. But that's just my retelling, because, like I said, I have not been very hands-on with that particular project.
It should be noted that Ethereum's switch to proof of stake has made them 99% more power efficient than proof of work.
Yeah, I personally tend to be a very big fan of DPoS systems, which Ethereum is not DPoS, but also like a lot of people come into blockchain and they're like, make everything decentralized, and then they go and it doesn't, like, the world currently is not a decentralized system, so why like make yourself do it, I suppose. But I'm getting a little bit more into personal opinion than like than than the actual theoreticals and the practical implementations there. But yeah, they seem to. Ethereum's also used as sort of like a hub. You know, it's the old technology. I know it's only been around for a decade, but like it's the Bitcoin and Ethereum are the old men on the block, and so. While people are building out these new chains that are, you know, more advanced, more powerful, faster, you know, more appropriately geodistributed or whatever, they a lot of the times still call back to Ethereum because Ethereum is still the common language. You see this with chains like Polygon, you know, where they have they're doing a lot of processing that is cheaper than Ethereum, but whenever everything's all said and done, they report some ticket or something to Ethereum as the single source of truth, as it were, in the big ecosystem of blockchain in general. So Ethereum as a chain and as a community is still relatively important, which is kind of interesting. So. I hope I didn't talk anybody's ear off or um, go down too many rabbit holes that were confusing.
No, it was great. Thank you, Caleb. Does anybody have any other questions?
None here in Greenville. Thank you so much, Caleb. We really appreciate it. It was very informative.
Yeah, absolutely.
Okay, thanks, Jace. Do we have a? I'll go ahead and stop the recording, and we can talk about what we're going to do next.